Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें band structure of materials at nanoscale विषय रे पढिबा which is same as the band theory of solids, right? So if we consider the electrons in an isolated atom, then they possess discrete energy levels such as 1s, 2s, 2p and so on. This is shown in the figure, right? So this is the energy levels for an isolated atoms for the electrons, right? Now these levels are filled with electrons in order of increasing energy, right? And when these isolated atoms combine to form a solid, remember whatever the solid, liquid or gases, suppose we consider solid, okay, it is a combination of atoms. So similarly when these isolated atoms combine to form a solid, then they arrange themselves in an orderly pattern, and this is what we call a crystal, right? Now in a crystal, due to the periodicity, each atom is in the electrostatic field of the neighboring atoms, okay? सबु जते प्रत्येक एटम अछि से नेबरिंग एटम रो इलेक्ट्रोस्टैटिक फील्ड रे रहुछि, right? Now the discrete energy levels of individual atoms are no longer valid. Instead, due to the interaction, because जो neighboring atoms सहित interaction जेतो होछि, okay, so that the discrete levels now split into closely spaced sub levels, okay, as you can see in the second figure. These are the splitted levels, okay, and it is occurring at the higher levels, right, not at the lower levels, right? Now the number of sub levels will be equal to the number of atoms. Suppose it is capital N, so the number of sub levels will be equal to the number of atoms n in the solid, and since this n is very large and it is of the order of 10 to the power 23 per cc, right? Therefore the separation between these sub levels will be very small, okay, just the reciprocal 10 to the power minus 3 electron volt. This will be the separation between the sub levels. Hence these sub levels are almost continuous, right, rather than your discrete. agro jemti discrete thila ebe ei sub level mane continuous he jibe in the energy, and thus they are said to be energy bands, okay? ei sub levels ko ame energy bands boliki kahiba, okay? Now the first energy level of various atoms constitute the first energy band, and the second energy level similarly will form the second energy band, and so on. Now the energy band which is formed by the valence electrons, okay, valence electron द्वारा जो energy band create habo, that will be called your valence band, right? Similarly the band in the next higher band will be your conduction band, okay? Conduction band is the band which is actually normally empty, right? And this valence band is the highest occupied band, remember this thing, okay? Valence band hochi the highest occupied band, and the conduction band is normally empty, right? Now these allowed energy bands are in general separated by a gap or a region which have no allowed energy states, okay? And such region are called your forbidden gap or forbidden energy bands, okay, or simply energy gaps, right? देखो आ गोटे जिनस जमती कहली मु lower levels like your 1s and 2s, you can see there is no splitting, Okay, the splitting of energy levels does not take place for the lower levels 1s and 2s. Why so? Because the electrons in these levels are being deep inside the atoms. Suppose this is the atom. Okay, at the center we have the nucleus. Now the electrons are revolving around the nucleus, right? Now for 1s and 2s we have the electrons are in the first orbit, right? So these are inside the atom, or you can say these are in a greater influence of this nuclear attractive electrostatic force, which is the Coulomb force, right? So that they are significantly less affected, or you can say not affected, by the presence of other atoms. Further, the 2p level also is not splitting. It will split actually until when the interatomic separation becomes smaller than, which is actually found in case of your sodium, that is Na. Okay, তাহলে যে কি এই 2p লেভেলটা স্প্লিট করিব. So normally we can say this 3s level actually is the first occupied level, which is to be splitted into sub levels or bands, right? So in the higher energy levels the splitting occurs because of electronic wave function which overlap significantly. Okay, as you can see in the bottom figure here, higher energy levels like your 3s 3p, the wave function are actually overlapping significantly in order to give rise to the interaction between them, right? So in this figure we can see the splitting of various energy levels in terms of your interatomic spacing. Okay, here in the x-axis we have taken the interatomic separation or interatomic spacing, and in the y-axis we have taken the energy, right? So this is the case for your 2p level. Then this is the 3s, right? This is the 3s. Now this is the 3p. So देखो এই জায়গায় overlapping হচ্ছে. This is the overlapping region, right? Now on the basis of this band theory we can classify these solids into three categories: conductor, insulator and semiconductor. This you have also read in your +2, right? So let us distinguish between the conductor, insulator and the semiconductor on the basis of the band theory, right? So the energy band structure is actually the characteristic feature of a solid, and different solids possess different band structures, which gives rise to a wide range of electrical properties which are observed in them. Now depending upon two things, the nature of band occupation by the electrons and the width of the forbidden energy bands, that is the forbidden gap, we can classify the solids into three types, that is conductors, insulators and semiconductors. So let us study them one by one. First is your insulator. Okay, so here insulators are those substances in which the valence band is completely filled with electrons and the conduction band is empty. Okay, and the gap between these two, that is your forbidden energy gap, is large. It is around 5 electron volt or more. Okay, so it is shown in the figure at the bottom, this one. So you can see this is the filled valence band having energy EV, this is the empty conduction band having energy EC, and the gap between these two is your forbidden energy gap, which is suppose having energy EG, which is greater than your 5 electron volt. Okay, now because of this large gap the electrons cannot thermally excited easily from valence band to your conduction band, right? And therefore the external electric field, which is your electric potential, cannot cause any significant current, because current is nothing but your flow of electrons. Okay, it is the rate of flow of charge, right? So electrons ଯେତେବେଳେ ଯାଏ ଏଇ valence ରୁ conduction band को ଯେହେତୁ ଯାଇ ପାରୁନି, so electron flow ହେଇ ପାରିଲାନି. Okay, so that current ମଧ୍ୟ create ହେଇ ପାରୁନି, right? So for this reason the electrical conductivity of these materials, which are your insulators, is extremely small. Okay, and may be regarded as in fact zero. right? It is nearly equal to 0, the electrical resistivity under ordinary condition. Okay, example jodi ame kahiba ethi insulators ro, like your NaCl, then diamond. These are good insulators having a forbidden gap of around 6 electron volt. Now when the temperature of the insulators is increased above your room temperature, then some of the valence electrons may acquire enough energy in order to cross over the gap, okay, and go to the conduction band, and it will give rise to extremely small current. Okay, so the resistance of insulators decreases slightly with the increase in temperature, and thus the resistance of an insulators have negative temperature coefficient of resistance, right? Now the second category is your conductors. So conductors, you know, particularly suppose we say in case of your metals, okay, metals are very good conductors, okay, and these are the substances in which the bands either overlap or they are only partially filled, okay, as shown in the figure. This is shown in the right side figure, okay. So देखो एटी overlapping ହେଇଛି, okay, upare ethi valence band, this one is the valence band, this one is the conduction band, and this is the region of overlap, right? This is the first possibility. Now the second possibility is partially filled, means the conduction band is partially filled and valence band is filled, right? So this is the case of your conductor, okay. Thus the electrons and the empty energy states are intermixed, okay. This will be intermixed within the bands so that the electrons can move very easily, okay. It can move freely under the influence of external electric field. So for this the metals have high electrical conductivity, but however their conductivity decreases with the increase of temperature, right? The electrical resistance or resistivity in case of your metals increases with the increase of temperature due to increased number of collisions. Mane rakho, as we increase the temperature, there will be increase in the number of collisions at the higher temperatures between the electrons, right? Hence the metals have a positive temperature coefficient of resistance. Now due to overlapping, the valence band also acts as your conduction band, right? Now to make things more clear, let us take for example the case of your sodium, okay. Sodium, as we know, Na, it will have atomic number Z equal to 11. Our electronic configuration here rahigala 1s2 2s2 2p6 3s1. Thus the valence band, which is formed by the 3s level, as we are saying in the band structure, so 3s level re valence band create hela, which will be partially filled. Now on application of electric field, the electrons can freely move into the empty states within the same partially filled band, okay. So partially filled already अछि, आउ सेतिरे जो पार्ट टा खाली बा एम्प्टी हे कि अछि से आडको इलेक्ट्रॉन माने इजीली मूव करि परिबे when we apply electric field. So this makes the sodium a very good conductor, okay. Another metal, if you take suppose magnesium, so it has atomic number 12. Now the electronic configuration is 1s2 2s2 2p6 3s2, okay. It is also a good conductor because here there is overlapping of 3s and 3p bands, okay. So again current flow is possible in presence of this external electric field. Thus the observed electrical properties in case of your conductors, or better to say in case of your metals, can be explained on the basis of their band structure, right? And in the figure 2.10c, the conduction band is abbreviated as CB, and whereas the valence band is your VB. Shortcut रे हमें याको conduction band को CB, valence band को VB बोले के लिखुचु, right? अच्छा. Now finally in the third case we study about the semiconductors, okay. See here the band structure is similar to that of your insulators at absolute zero temperature. That means it will have a filled valence band which is separated from an empty conduction band by means of a forbidden energy gap which has no allowed energy states. Okay, let us analyze it in the figure. So you can see this is the case of your semiconductor having filled valence band, empty conduction band. But if we compare this with that of your insulator, the difference is that insulator is having a forbidden energy gap greater than 5 electron volt, but in case of your semiconductor, this forbidden energy gap is much smaller. It is around 1 electron volt. Okay, suppose for example we take silicon. It is a semiconductor and it has a forbidden energy gap about 1.1 electron volt, right, as compared with that of your diamond which is having 6 electron volt of forbidden energy gap. Diamond is a insulator, right. Some other popular semiconductors are your germanium. Okay, GE. It has a band gap which is also very small, around 0.72 electron volt, right. Now due to the relatively small band gaps of these semiconductors, the electrons may be thermally or optically excited from this valence band to your conduction band. Thus a significant number of electrons now may be thermally or optically excited across this forbidden gap. Okay, so if the electrons are excited, then obviously we'll have current. Okay, so this excitation can be done at room temperature, right. So as a result their resistivity will decrease with the increase in temperature. Okay, now you can regard this semiconductor having a negative temperature coefficient of resistance, right. But however, if we take absolute zero temperature, then what will happen? The filled valence band will now have no empty states into which the electrons can move, right. And also the empty conduction band, there are no electrons which can move into the vacant energy states. Thus there will be no conduction at all on application of your external electric field at absolute zero temperature. Okay, so we can say the semiconductor will behave like an insulator at absolute zero temperature. Okay, we can relate this energy gap value, that is Eg, at absolute zero temperature and suppose at some ordinary temperature mathematically by using a relation which is Egt equal to Eg0 minus 3.6 into 10 to the power minus 4 into your T. Okay, and here Eg0 is the energy gap at 0 Kelvin, that is your absolute zero temperature. Egt होउची energy gap at T Kelvin, और T ହେଇगला the temperature, which is the increase in temperature. So clearly from this relation we found that the energy gap decreases with the increase in temperature. Okay, so after knowing this, let us have some knowledge about the Fermi energy and how is it related to the band structure. Okay, how the value of Fermi energy is differing for the case of your conductor, insulators and semiconductors, right. So the energy and volume density of electronic energy levels in a crystalline solid change across the energy band. Now the number of electronic energy levels which are corresponding to the electronic wave function in case of your solid crystal in the central region of the band are expected to be very large, okay, which is shown in this figure. So in this figure we can see the density of states across this energy band, it is coming out to be like this. Okay, this is the variation of density of states across the energy, right. Density of states विषय already आमे previous class रे पढ़ी सारिछु. Okay, it is defined as the number of electronic energy states per unit volume per unit energy, right. So density of states raw value for the case of suppose 3-dimensional bulk material, यार expression हमें previous class रे पाई थिला like this. Similarly for the case of 2-dimensional quantum well, this is the expression. Okay, it is having a heavy side or unit step function, right? Then for the case of one dimensional quantum where this is the expression, and finally for the case of zero dimension structure like your quantum dots, this is the expression for the density of states. Okay, so after having all these expression, we can see for three-dimensional case the density of states is proportional to the square root of energy. For the case of two dimension, it is like that of your staircase, actually inversely proportional for one step. Okay, e to the power 0 is constant. Okay, but at the other step it will have a gap of m by pi h cross square. Okay, for reference you can see my previous lecture. Okay, now for one dimension, it is again having a step size and it is inversely proportional to the square root of your energy. And in the case of your zero dimension, it is proportional to the delta function of your energy, right? Acha, etki jani sarila pore, now the electronic state can be occupied by an electron or unoccupied, and the counting statistics of concentration of electrons in a band is based on this formula. The number of electrons in a band must be equal to the product of number of states in the band and the probability of occupancy of that state by an electron. Okay, now an energy state, suppose having energy E, has a definite probability which is to be occupied by an electron. Okay, and it is given by the probability of occupancy, this is the function Fe. Okay, so this probability of occupancy is the main conclusion of your Fermi-Dirac statistics. Remember, electrons are fermions, so that they will obey the Fermi-Dirac statistics, and this function Fe is known as Fermi distribution function. Okay, hence the number of electrons over the energy interval, that is between E and E plus dE, its value will be rho E dE into Fe, right? Therefore, the total number of electrons in a band will be obtained simply by integrating this over the top, that is Et, to the bottom, that will be Eb. Okay, this has some printing mistake, it should be Eb, right? So top of the band and bottom of the band, this should be the limit of integration, and upon integrating we will have the total number of electrons in a band, right? Now the number of conduction electrons in the conduction band of the semiconductor at a temperature T, this is given by this formula, n equal to Ec up to infinity, this will be the limit, then rho E Fe dE. Similarly, the number of holes, because when electrons are going from valence to conduction band, it is leaving behind a vacant space. Okay, this you have read in your +2. Okay, so this vacant space is doing what? It has the same characteristics as that of your electrons, but the only difference is that its charge is positive. Okay, although its magnitude is same as that of your electron, but the charge is opposite to that of your electron, so it is positively charged, and this we call as holes. Okay, so the number of holes which are present in the valence band at temperature T, this is given by the formula P equal to from minus infinity to Ev. Okay, Ev hoji energy of your valence band, then rho E into 1 minus Fe dE. Remember, this is 1 minus Fe, this is Fe. Okay, so we are simply doing this by the method of probability. Okay, the probability of having anything is suppose Fe, then the probability of having nothing will be 1 minus Fe, simple. So the Fermi-Dirac distribution Fe applies to the case of fermions, as I have told, because electrons are fermions. Okay, and the particles which are under this fermions category, they will have half integer spin. Okay, which must obey the Pauli exclusion principle, right? So each type of distribution function has a normalized term which is multiplied with the exponential in the denominator, and which may be temperature dependent. Okay, so for Fermi Dirac distribution function, that terms usually written as e to the power minus EF by kT. This is where the Fermi energy is coming. EF is the Fermi energy and K is here the Boltzmann constant. Its value is around 1.38 into 10 to the power minus 23, right? And T hochi eti absolute temperature. So that the Fermi Dirac distribution function will be Fe equal to 1 by 1 plus exponential of E minus EF by kT. Okay, so this exponential, actually there should not be another E. Okay, this has some printing mistake. Okay, I will edit that. So this Fe is the probability of fermion with energy E, and the term 1, actually this term 1 is appearing in the denominator due to the fact that the particles are indistinguishable. Remember, fermions are indistinguishable. Okay, so you have also read this about the fermions in your statistics. Okay, so at absolute 0, that is when T equal to 0 Kelvin, then what will happen? This Fe will be equal to 1 when E is less than EF. Okay, so when E is less than EF, then E minus EF becomes negative, right? So that e to the power minus infinity becomes 0. Okay, so 1 by 1 will be equal to 1. Now at T equal to 0 Kelvin, but E is greater than EF, then what will happen? This term will be equal to infinity, right? So that this Fe will be equal to 0. 1 by infinity is 0, right? So we consider all the energy levels up to the Fermi energy are filled and no particle has a greater energy. So Fermi energy is the energy of the topmost level, right? So this is wholly consistent with the Pauli exclusion principle, where each quantum state can have only one particle. Okay, so let us see the figures. The temperature dependency of Fermi function is shown in the figure. This is the first figure where the Fermi function is varying from 1 to 0 at absolute 0 Kelvin. Okay, now above this absolute 0 Kelvin, okay, slightly above this 0 Kelvin, we are noticing some deviation, right, from the Fermi energy. Okay, so this is the deviation which is around 2 kT, and when the temperature is beyond the 0 Kelvin, then the graph is coming like this. Okay, so this is again your 2 kT. This is the deviation, right? Acha. Now let us study the variation of this Fermi energy for the case of conductor, insulators and semiconductors. So first, in case of your conductors or metals, the Fermi energy is defined as that energy for which at T equal to 0 all the energy levels below the conduction band will be filled and above the conduction band will be empty. So the variation of this Fermi Dirac distribution function with respect to energy is like this. Okay, this is for T greater than 0, and the conduction band is obviously partially filled. In case of metals, the Fermi energy is the highest occupied energy level, right? Now in case of your insulators, actually insulators रे एठी Fermi energy टा रहिबो in the midpoint. Okay, this is lying in the midpoint between 6 to 10 electron volt. Okay, the gap is 6 to 10 electron volt and the Fermi energy in the midpoint. This is the valence band which is completely filled, and the above one is the conduction band which is completely empty. The variation is quite similar. Okay, now for the case of semiconductor, right, semiconductor, suppose we take intrinsic semiconductor, then the Fermi energy lies in the middle of the again forbidden gap. Okay, but we have now two cases because we are studying the semiconductor, so that for electron we will have a variation like this. Now for holes we will have the opposite one because the holes have a variation of 1 minus Fe, right, as we have studied in the formula. Okay, so this is the case of intrinsic semiconductor. Suppose we make it extrinsic. Okay, so extrinsic केमती आमे करि परिबा by means of doping. Suppose we mix a trivalent impurity, then it will become p type, Then suppose trivalent impurity is your boron. Okay, we add it to the silicon lattice. The variation will be like this. Again, the Fermi energy, you can see it is closer to the valence band, right? Now if we add a pentavalent impurity like that of your phosphorus to the silicon lattice, okay, this is the phosphorus, the variation will be like this, and now the Fermi energy level is nearer to the conduction band. Okay, so why is it happening? Because suppose in case of pentavalent impurity we have 5 electrons, out of which one electron will be weakly bound, okay, because it cannot make pair, right? So that it will be free with the donor energy level just below the conduction band, and these electrons can easily be transferred to the conduction band, so that the Fermi energy level is shifting towards the conduction band. Similarly, in case of your trivalent impurity, now we have shortage of electron, so that it will create holes, okay, free holes, right? The missing electron will produce an extra hole with the valence band, and these holes in the valence band will increase the conductivity. Remember, in case of your pentavalent impurity, that is n-type semiconductor, the conductivity is increased by the extra electron, and in case of your trivalent impurities, that is your p-type semiconductor, the conductivity is increased by the holes, so that the Fermi level will shift or move towards the valence band, right? At the end, ମୁଁ ଏଠି ଏଇ ଯେଉଁ ନାନୋ ମେଟେରିଆଲର ବ୍ୟାଣ୍ଡ ଷ୍ଟ୍ରକ୍ଚର ଏଇଟା ଆଉ ଗୋଟେ ବହିରେ ବି ଲେଖା ଏଇଟା ଥିଲା, ସୋ ୟୁ କ୍ୟାନ୍ study it for your knowledge purpose and make your note precisely, and you can summarize it point wise, right? Actually the writing is very much similar. As you can see, this is the isolated atom having degeneracy, thereafter the energy gap is coming out, then the degeneracy and non-degeneracy of the p electrons, okay, so that you can see this is the splitting. Okay, now accordingly it is giving some of the examples of like that of your carbon, germanium, then the energy band gap, okay, this is the band gap between the conduction and the valence band. Okay, thereafter it is classifying the three types of your solids, that is your metals or conductors, then semiconductors, then insulators. Along with that, it is giving some of the examples of these three types, that is your insulators, then semiconductors, then your conductors or metals. Okay, so you can also study it for your knowledge purpose. Thank you.